note that you're not doing it splitting. A cell at address X that points to A cell at address Y pointing to A, okay? But you're talking about the same heap in both cases, right? So this can only ever happen if X is equal to Y, okay?
Florian, can you close the door?
Okay, now this is this full kind of language is too difficult to use for tools. So most automatic tools actually use a fragment, a syntactic fragment that's called symbolic heaps. And that's because basically the formulas in this fragment look like slightly abstracted models. They are almost into one-to-one correspondence with the models on the the left-hand side. So this fragment is basically a classical conjunction of some formulas and a star conjunction of some other formulas. And the kinds of formulas we're allowed to put here, the kinds of formulas we're allowed to put here is restricted. Okay, so in here we're only allowed to put either equalities between program variables or disequalities, nothing else. Okay, so from the get-go, we've pushed negation basically down to the atomic level. We don't have unrestricted negation. We don't have disjunction. And we only have these kind of equalities and disequalities that we're allowed to classically combine with conjunction. The star part is only points to's and inductive predicates, of which I will, like the list thing, okay, which I will talk about a bit later. But for now, this you can think of this as the spatial part, because it's talking about space, it's talking about the heap only, and nothing else. And this is only talking about pure facts that are independent of the heap. They're only dependent on the store. Okay, and that is why this is like the store and this is like the heap. They're abstract descriptions of the store and the heap, and that's why this is called symbolic heaps.
Still, I don't understand the symbolic. So is this the same as like symbolic mode checking? Or?
No. Symbolic as in we use formulas to describe the model.
Ah, okay. So basically this one
so you
defines a model.
It describes a set of models that satisfy it, right? But it is very close as a notation, it is very close to a model itself, right? Because with the exception of the crazy things you can do with inductive predicates, but if you omit those, then you have basically an almost kind of Boolean correspondence with models.
The problem that if you have a large program, does this mean that your formula is quite large? Or?
Of course, yeah.
But this is kind of like a very early way of doing the program modification. So you encode the model as a formula, then you play with the formulas. No. So we're not going to do that. What is done generally is to abstract the program state using these formulas, and all the game will basically end up happening here, because you're not gonna. Otherwise, we would only be able to speak about finite collections of cells, right? So, bounded collection of cells, I should say. So, you would never be able to say, I have a linked list of arbitrary size. You'd only be able to say, I have a list of size 1 or of size 2, right? So, in order to have that ability, we have these inductive predicates, and that's where things get interesting. Okay, so this is an example formula. X is null, y is not equal to z, y points to z, and disjointly there is a list starting at y. There's a linked list starting at y. At z, sorry. Can't read. Okay? So this is the spatial part, the star conjunction, and this is the classical conjunction of equalities and disequalities between program variables. Okay, now what is known about this fragment?
and I will mostly ignore well, actually, separation. I'll start with separation logic. So undecidable, full separation logic. Well, this is not surprising because it includes first order, right? So from the get-go, the full thing is undecidable. If we throw away the quantifiers, it's still undecidable. Okay, if no exists, no for all. It's still undecidable, and the main reason is that magic wand. I'm not going to say much about it. If we throw away the magic wand and keep the quantifiers, it's still undecidable. Okay, because the quantifiers plus the star still. Remember, this is not exactly first order because we've thrown away all functions and all relations apart from and constants apart from the points too. Okay, so we can't necessarily obviously encode everything in first order logic in separation logic anymore, right? So these two results are actually not trivial. Now, what is decidable? Well, if we have no magic wands and no quantifiers, but otherwise arbitrary negation, conjunction, disjunction points to, then that's p-space complete. Okay, so that's kind of an early result. Now, if we focus down on symbolic heaps, so the fragment that only basically has conjunctions and things, and we only allow the points to's and the list predicate, then entailment and satisfiability is in polynomial time, quite recently shown. Okay, so if you only want to reason about lists and single cells, then everything, all entailments are and satisfiability is decided, and in polynomial time, no less. If we allow existential quantifiers but no lists, then we jump up to pi2. So it's kind of quite a bit of a jump. It's basically a sort of matching problem because you can have lots of points twos on your left-hand side, lots of points twos on the right-hand side, and if you put enough existential quantifiers on the right-hand side, then you're kind of forced to play this matching game that basically blows up into the second level of the polynomial hierarchy.
So I'm sorry, pi2 means it's...
Pi2 is NP to the NP, let's say. So if you had an NP oracle, you'd still need NP time to solve the problem, or co-NP, whatever. Symbolic heaps, so the same thing, but if you add the list predicate, is still pi2 complete. So at least from the theoretical complexity point of view, no big harm is done by adding lists. But what about symbolic heaps with general inductive predicate? So what is general inductive predicate? It means this kind of thing, this kind of fragment, but where this inductive predicate is user specified. Okay, we don't fix it beforehand and we say you can only reason about lists. Okay, we give a mechanism for defining inductive predicates and we say go and define anything you like to your heart's content using the predicates. Then what happens? Okay, so now I'm going to start talking about slightly more involved stuff, and this is kind of the interesting big IP. So this is an example of a way to formalize the definition of a linked list. So I have a linked list starting at x, if x is nil. I use nil here to not avoid using the program null. Yeah, but otherwise it's just a non-allocated address. Nil is a special constant that is never allocated. Okay, so it's exactly the same thing as null. So either x is nil and the heap is empty, meaning I have an empty list basically. Okay, it's a nil terminated list, or second choice, x is allocated and points to the value y. Okay, so the contents of the address x is y, where y here is basically existentially quantified. Okay, so we're making the assumption that just to save on notation that all the variables on the left-hand side of an inductive clause that are not in the arguments are extensively quantified. So I have a cell at X, it points to Y, and there's a list at Y. Okay? So I make one step ahead and then I recurse using the definition I already have. Is everyone kind of happy with this as a definition of what a linked list is? Notice that this forbids certain kinds of cycling. Okay, the star here avoids the possibility where I might go and link back to the beginning, right?
So it also separates that problem, isn't it?
Exactly, and that is what I didn't say because I didn't want to spend too much time about why separation logic is interesting from that point of view. But it's exactly so it forces the two parts, the two formulas, to never alias, to never share memory.
But
okay.
If I do want to express like a circle, what's the name? Circle link.
It is possible. You just need an extra option.
Okay.
Well, if you don't want to spend too much time on this, but because I'm already running late, but so you can have okay. Let me carry on a bit, and I'll come back to this because I need the list segment. So list segment is a generalization of the linked list, but that it isn't necessarily nil terminated. Okay, it terminates at a known address. So it starts at X and it terminates at Y. Okay, so it's just you take a linked list and then you chop the prefix off, and that bit is a linked list segment or a list segment. And the definition for that is that either X is equal to Y and nothing is allocated. Okay, so you have an empty list segment because your 2 pointers are equal. Or you have a chain, so you have a X points to some value Z, and there's a list segment starting at Z and terminating at Y. It's the same thing, just generalized at its end point. Okay, so now having the list segment, we can express the circular list by saying I have a circular list at X if X points to Y, and I have a list segment from Y to X. Sorry, from Y to X. Okay, so this is a circular list. Yeah? So there's a cell containing Y at the address X, and then from this there's a list segment that ends at X again. And that's you just have to basically kind of reify one part of the one cell of the list and keep it separate. Okay, and this is an example of a binary tree. Either my tree is empty and my pointer is nil, or the tree is not empty and the address X is allocated, and it has two fields, the left and the right pointers. Okay, so Y is the left tree, Z is the right tree, and everything is starred together. So I have a binary tree at Y, binary tree at Z, and because I'm using stars, I cannot have a DAG. Okay, so this situation where you have some tree and then you have some sharing that leads you to a DAG, and that possibly terminates at nil, is forbidden exactly by using these stars. Okay, so if you have an algorithm whose correctness crucially depends on actually running on a tree and not on a DAG, that will help you a lot. Okay?
Could you extend the B tree in the same sense you've extended the list with the else segment to introduce some sort of sharing?
Correct. Yes. Well, this isn't about sharing, right? I mean, this is about. Is that what you mean? The segment.
Yeah, yes, the segment. I thought this was kind of.
So you can generalize the binary tree to a binary tree segment, but that still doesn't. Well, you'd have to be explicit about sharing, let's put it this way.
Okay.
You'd have to use classical conjunction to allow sharing. Okay, if you allow classical conjunction in the spatial part, then you get sharing, but then you get all the monsters as well. So the computation wise. Okay.
Nikos,
Yeah.
I have to go. Can I ask you a quick question before? So I somehow have trouble understanding this either from a proof theoretic point of view or from a semantic point of view. I mean, you presented
So any point of view, yeah.
Yes, but this, I mean, you presented some semantics, but is there some kind of more denotational semantics or?
It's a logic, right? I mean, I didn't
Yeah.
talk about the program logic
Yeah,
of the
yeah,
here.
sure,
I'm
sure.
just talking about the assertion logic, right?
Yeah.
Denotational semantics for the assertion logic, no. There are denotational semantics for the program
Program
logics
stuff.
built on top
Yeah,
of
sure.
this.
And proof theoretically is, I mean, is extension of?
Proof theoretically, so separation logic is a kind of specialization of the bunch to implication family of logics, which itself is a kind of relevance logic.
Okay.
If that, so you have multiplicative connectives.
So
right?
you don't have contraction, but you have.
Exactly. Exactly, yeah. So star and the magic one are multiplicative connectives, and you have some similarities there with linear logic, but also some very distinct differences from a proof theoretical point of view.
Okay. And so my question about negation was actually to do with these connectives rather than the connectives on your store. I was sort of talking about. Is there
So
a
symbolic
negation for these?
So the symbolic heap fragment explicitly disallows negation on the spatial part.
Okay.
And that is because it is not only computationally bad to have a negation attached to a spatial fact, but it also doesn't really occur in program proof very often that you want to say, I don't have a list here. I have something else. I don't know what it is, but I don't have. What I do know is that it's not a list. That is rarely useful. Right? So that is why negation is just restricted to the pure part, basically. Okay. Shall I? Okay. Now. This validity for this fragment is undecidable. So, in other words, if you say, does P entail Q, where P and Q are arbitrary inductive predicates defined with this kind of schema, then unsurprisingly, to decide whether one entails the other is undecidable. Can anyone think of an easy way of showing that? No, it's only one part of a longer paper. So you can easily encode context-free languages using recursive definitions, right? And points to. So points to's, you can say X points to some symbol in my alphabet and some pointer that continues the chain of symbols. Okay, and that way you can start encoding strings, and then you can basically sort of take the rules of the context-free language and map them to rules that define inductive predicates. And then we know that context-free language inclusion is undecidable, so therefore entailment naturally becomes undecidable. However, we can still do some stuff. The crucial thing here is that all these things point to induction, right? So when you're trying to prove a fact about these things, you have to resort to some method, some proof method that is akin to induction, okay? Because these are list fixed points, if you like. Okay? And one of these methods is cyclic proof. So I'm going to run you through very quickly through a proof that if you have a list segment from X to Y, and Y is a lone cell pointing to null, or nil, then the whole thing from X to nil is a list segment. Yeah? Does that kind of make sense? If you have a list segment from X to Y, and there is only one more cell that ends in nil, then the whole thing is also a list segment. Okay? So what I'm going to do is use the definition of the list segment. These people do. So remember, there were two clauses defining what this list segment is. Either it's empty, or it's at least of length 1. Okay, so I will replace this left-hand side list segment with the two possibilities. And I will get two premises that I have to prove both here, right? Because it's on the left-hand side. So either x is equal to y and the list is empty, or x points to some value z and there is a list segment from z ending at y. It's an interesting, more interesting workshop going on next door.
Beautiful workshop.
And that's like a left unfold rule. So I've unfolded the definition of the list segment that I have on my left-hand side. And I got two new goals to prove. The left hand, this branch is going to be easy, right? This is like our base case. So I sort of get rid of I rename things to x here using the quality. Yeah, so I just keep x because I don't really need y. And I unfold the right-hand side now to only one of the clauses. And I choose which one, right? So I'm playing a kind of non-deterministic game here, where because it's on the right-hand side, I only need to choose one, right? I don't need to show it for both clauses. So I choose the clause that says this list segment is not empty. Well, why do I do that? Because I see that my left-hand side is of size at least 1, right? So it can't really be empty, the right-hand side. So I end up with a cell at x and another list segment, and then I do another right unfold, assuming this list segment is empty. Okay? I'm not going to bore you with the details, but basically this is a very easy branch to prove because it all boils down to saying that one cell is equal to one cell. Okay? So base case, nothing amazing. Kind of first order manipulations here, nothing new. Okay, now let's look at the other side. I right unfold again. So here I want to say that I have a cell, I have a list segment, and then another cell, and I want to show that the whole chain is a list segment. Okay, that's what I want to show. So what I'm going to do is unfold the right-hand side again by choosing the clause that says it's not empty. And I get this kind of thing, and then I have an existentially quantified variable here, w, that I'm going to choose to instantiate with z from the left-hand side. Why? Well, the left-hand side says that x is allocated and its value is z, and the right-hand side says that there exists a w such that x is allocated and points to w, right? So really there's only one choice for this instantiation, okay? That's again a first order kind of trick, nothing amazing. Now, what I'm going to use is a rule that has to do with separation logic proof theory, which allows me to subtract the same points to from both sides. Okay, I have it on both sides, so I can strip it off, and it starts with everything else. So there's a star introduction rule that allows me to produce another goal that says there's a list segment from Z to Y, and then there's a cell at Y that points to nil, and there's a list segment from Z to nil. Okay, so the same thing, but I just stripped off the allocated cells at X. And now what I'm going to do is again a very obvious first order trick, which is just a variable substitution. So I'm going to rename Z to X. Okay? Very kind of easy stuff, nothing amazing. I think that's the only thing I did, by the way, right? Nothing else changed. Two goals are the same. And now what I'm going to say is I'm done, because this is the same as that. And I'm going to create a cycle here. Okay? And now I don't have a proof tree anymore, I have a cyclic graph, proof graph. Okay?
But this is just an oscillator way of X point.
Yes.
Because you have a list of X point, so you just...
No. Well, I mean, so I can prove false, right? Because false because of false, and then a cycle, and it's not exact. There's stuff missing. That's what I'm kind of pointing out to here. That does that? No, that doesn't answer your question. What do you mean?
Well, so basically you have this. So, I mean, it seems that this just reminds me something. I mean, for example, in process algebra, so if you have this kind of, recursion, and they always have this kind of proof, but in that case, they want to prove that the two terms are equal or not. Yeah. So this is called fixed point induction.
No, it's not fixed point induction. It's so in fixed point induction you don't have to do anything extra. Now here we still need to do anything extra because, like I said, you could prove false, you know, just by assuming false and making a cycle, right? That's not a sound proof. We don't want this to be a sound proof. Yeah, do we agree on that? I hope.
Yes.
Okay, if this is a liability of my proof system, then I'm still not done in showing that this is sound. Okay, and what I'm going to say next is that I can trace an inductive predicate through the proof. Okay, that any infinite path through this graph will have to unfold infinitely often. Okay, so here I'm doing an unfolding step. Right, this line here. Any infinite path through this cycle will go through this step an infinite number of times. Yeah, simple stuff. That means that if, by contradiction, you know, reasoning by contradiction, if I could generate, semantically speaking, an infinite path, then I would have at least fixed point that is unfolded an infinite amount of time, infinitely often, right? Which is a contradiction, right? But that relies on my ability to find this trace, right? If I cannot find this trace, I don't have a sound proof. I have a closed proof, but it's not sound. Okay? I don't want to dwell too much on this. The model checking is an extra, you know, showing that these traces exist, showing that these weaknesses of soundness exist, is an extra process that has to happen on this object, on this cycle, this kind of cyclic proof, and it is a p-space complete problem, no less, right? It's not just because you have this, you're not done.
So model checking means that you have this. Okay, so every step you can apply some rule, then you can form this kind of graph, and each node of this graph is kind of proof obligation. Then you search whether you see some like working condition whether you can read this infinite often.
Yeah, exactly.
Okay.
What's the last bit? You do something infinite often. What was the condition?
You have to check whether you can read this like red notes infinite often.
So there are. I didn't want to show this, but you made me. So there are proofs like a natural number is a number that is even or odd is a natural number, right? Yeah. So this is a kind of proof that you end up with a cyclic proof that looks like this. A nice butterfly, because the even case turns into the odd case, and the odd case turns into the even case. And that is a graph that has an infinite number of distinct infinite paths, right? There's not just one infinite path like this case. Here, you can do 10 cycles on one side, and then 10 cycles on the other side, and then 11 cycles on the right-hand side. You know, do you see what I mean? So you have an infinite family of different infinite paths, and you have to show that for all of them there is a witness, and that you actually have to go down to the model checking. You cannot just say, oh, I have a simple cycle and therefore it's done. Okay, now and I've been okay, so I've been working on a theorem prover called cyclist that finds this proof and model checks it and so on and so forth. And this is being used now to to prove separation logic as well. So you can, this is a, by the way, cyclic proof is something you can apply to any logic. It's not just separation logic, right? Because it's purely about fixed points and inductive predicates. Anyway, so that's one of my kind of hobby horses. A theorem prover that does this kind of cyclic proof.
So how do you do this? I mean, so do you, for example, I mean, I could imagine just one way, so we can do this kind of randomized search, then you can find the...
So are you asking about how the theorem prover finds this proof?
Yes, I mean this cyclist, how does it work?
So basically it has a bunch of rules that lets you explore the proof space.
Yes.
And it does a sort of depth first search, iterative deepening sort of search. But with this kind of ability to backlink. So it looks for substitution instances of things it has seen before.
But did you try this, I'm just out of my curiosity, did you try this like this fancy like A-star algorithm? It's basically this is like a graph search for...
A-star would work if you could assign costs to everything. And yes. I don't know what is the sensible way of assigning costs. We can, you can, just kind of like very superficial, like thought you can say that, okay, if there's, because you want to find this kind of sub-formula, then if this occurs, then probably you have, I don't know, more weight to go to that direction. This more or less like, you can form a kind of micro chain. You have a high probability to search this direction. How would you choose that direction? I mean, the whole problem is that when you start off a branch, you don't know that you're going to backlink back to here. You may backlink here, you may backlink here, right? So whose substitution instances are you going to look for? Unless you can,
It's gone 1/4 I know. Sorry, you guys should talk about this later.
Okay. I know. I will. So, okay, I'll skip this part. I'll just say, it's X-time complete. Any surprise? You know, you have a validity problem that is undecidable. You have a satisfiability problem that is decidable. No? That's because basically so in first order logic the two are identical, right? Because you can turn a validity question into a satisfiability question. You can always turn a satisfiability question into a validity question, I suppose, most of the time anyway. Here, this is not the case because we don't have implication, we don't have conjunction, we don't have classical conjunction over, unrestricted classical conjunction, and we don't have negation. Did I say that already? Yeah. So, we can turn validity into satisfiability, and that ends up being a good thing because we can solve the satisfiability problem. Okay? Now, I'm not gonna go through the whole thing. I'm just going to jump to the end and state. Yeah, whoop. I always do that. Okay, so lots of problems because so separation logic has been studied for the last, say, 2 decades. Okay, so even less than that. So there's lots of problems out there that are open. People generally are moving towards an SMT style situation. So if you're not familiar with SMT means satisfiability modulo theories, which has been an extremely successful theorem proving method for first order extensions, and people just use them as black boxes nowadays, the tools that do SMT proof. And it seems like that separation